told you there was going to be 3 lectures on circles and ellipses. We're on the second one tonight. That means that next week we're going to try to wrap up all of the problems of circles and ellipses. I'm going to try to explain to you 2 solutions to 2 problems that can drive beginners crazy. These problems drove me crazy when I was doing drawings where I needed to solve these problems of ellipses and did not know how. Problem number 1, I'll get to problem number 2 in about 20 minutes, is knowing where the center of the ellipse and of the circle it represents is. And the second one will be placing the angle, but we're going to deal with this problem of knowing the center. What is an ellipse? It's a circle in space. That's right. So if you've got a circle to begin with, and then you tilt that circle, you are going to have something that will be shaped like this, and we call that an ellipse. That's the circle tilted back in space. You know how to construct one now. And you know that one of the most important things about them is that you have to construct them with these crosshairs. What is this line called? The minor axis. What is this one called? The major axis. Those must be at right angles to each other. And the whole ellipse is perfectly symmetrical. It is symmetrical from left to right and from above to below. And that there's a particular curve that ellipse could be, if it were tilted more, shaped like this. If it were tilted more severely. There's constant symmetry, though. Symmetry from left to right and top to bottom. There's constant symmetry with this circle. That would be if there were such a thing as a 90-degree ellipse, which of course there isn't because it's a circle by that time. That would be perfectly symmetrical all ways around too. What else is perfectly symmetrical, top to bottom, left to right, that we dealt with a few weeks ago? The square, not the cube, although the cube has squares in it. The square made up of right angles. It's not quite a square, right? A little bit too high. That's closer. Perfectly symmetrical, left to right, top to bottom, means that's got to match that. You've got to do the same thing there so that you've got these little crosshairs. And a perfect circle will fit inside a perfect square and be tangent right at those cross points. Now, I go through all that to make this point. How do you find the exact center of any square quickly? That's right. You make an X shape, or in other words, you run diagonal, straight line diagonal from corner to corner, and it will land exactly in the center. And that is the way you find the center of a circle, too. I mean, how can you find the center of a circle? You measure across. How do you know you're getting it exactly at the widest point? It simplifies the circle to put it into here, run diagonals, and that will be the perfect center, top to bottom, left to right. Now, the same thing that happens where you find the center of that thing when it's flat happens if you take this square and tip it into perspective, which means it will probably be shaped more or less like that. More or less, because it could be shaped like that, perhaps, right? There's a number of different ways it can be shaped, and we'll talk about the specifics of that later. But did you know that in perspective, imagine those are done in permanent felt tip marker, right? I mean, those lines, imagine those embedded on there. When you tilt it, what's going to happen? Go from that corner to that corner and that corner to that corner. That is going to be where the absolute center of that square is in space. Likewise, right? Imagine it actually painted on here. It's got to be there. And what happens when you put an ellipse in there? If you've got an ellipse in there, it's going to be built. Oops. I better do this on the larger one to make this point. If you've got a perfect ellipse in there, it will have a major and minor axis, remember, that's equal top to bottom. And look at where that major axis is. That should be the same height as that. Now, what do you notice about that? Anything make you feel uncomfortable about what just happened? Where that major and minor axis meet? It is not the center of this. In other words, when you construct an ellipse, you have to have symmetry top to bottom, left to right, right angles, constant symmetry, and you have to do that when you draw this, right? That top part and that, but that line where that meets, that cross point is not the center of the circle. The center of the circle is back here, and you'd find it by running those diagonals. Now, that can confuse you, but the thing to remember is this business of the major and minor axis, this business of these crosshairs, it exists for one purpose only: to draw the ellipse. It exists to draw the ellipse. It doesn't tell you anything about where the middle of the circle is. This is what I mentioned last week to explain this phenomenon. This half and this half are equal, right? Be looking up here. It's important that you're not drawing this because it'll go right past you. This half and this half are equal, correct? When you tip something in space, things that are closer to you look larger than things that are further away, which look smaller. So it makes sense that this half of that square, that half is going to look bigger than this half, which is further away, which looks smaller. Right? So you lose the symmetry of foreground to background. That becomes no longer symmetry. I mean, this is symmetry, and this ellipse is symmetrical, left to right and front to back. Otherwise, you can't draw it. But the thing it represents, the circle on the square, when you tip it in space, that center will crawl back behind the major axis of the ellipse. Let me explain to you why. I can show you with this diagram that all of the books have. Let's make a great big circle like this. Sorry if it's an ellipse. It's hard to draw a circle this close because you lose the ability to be objective unless I was to follow my own advice and do a perfect square first. But let's say that's the picture plane. We're looking down on it from a helicopter. We'll do our character here with the nose and the ears and one eye looking out like that. A guy with one eye looking at this big tilted record in space. Now, let's say that's the middle, the center of the circle. Look what happens. Where does he see that? Let's run a straight line from that point to his eye, and from that point to his eye, and you've got a line that makes that wide, right? This to this is how wide that line will look. Look, what will be the widest point that this character will see? Look at that. It will be up here and right here, right? He's going to see that. And do you see how this line, the point between there and there, is going to, even though it's shorter, to him it looks wider. Did that make sense? If I was to work bigger, you could see it a little better.
Like do you know that his field of vision, like?
It doesn't make any difference what his field of vision. I mean, I'm giving him a bigger field of vision than he would have.
Right to the left, like each point out.
I'm giving him a bigger field of vision than he would actually have, probably, to try to make this point. The point being, let me clean up these lines and see if it helps a bit. He sees the widest point as this wide, that long of a line. From that point to that point looks that long. But this area here, which is a shorter line, looks longer to him, does it not? Because it crosses the picture plane here, and then this one, not symmetrical enough, will cross a little bit there. So it makes a little bit wider line. If it confused you, I've got to move on. Page 83 of D'Amelio's book has several accurate line drawings to make that point.
Okay, I think I'm getting you. So,
Here's the way to see it. Look at this line right here.
Right.
Is this line right here. It's the center of the circle.
Right.
Notice that it's further back and therefore looks shorter than this line right here, which happens to be what? The major axis of the ellipse that we used to draw this thing. Okay? And I'm sidetracking here to explain the phenomenon, and this is not the essential thing. The essential thing is that when you are drawing a phonograph record or a pan pot or a knob with a keyhole in it, if you're close up on it, or any kind of handle, or anything that pivots, right, that goes around something else that's in space, you're going to have to use ellipses to draw that, right? You've got round things going on there with a phonograph record or a pan pot or whatever else. You've got round things there. How do you know where the middle is? If you've got a bucket that's got a handle on the middle part of the bucket, you've got to draw an ellipse for that bucket, but how do you know where the handle comes from? It does not come from this edge of the major axis. You've got to do that major axis so you get it accurate. It's going to come from the center, which is going to be a little further behind it because the front part of that bucket looks bigger because it's in space. It's bigger front half of bucket than back half of bucket, which means the point that the handles will come out will be right there. Now, I mentioned buckets and phonograph records and everything else, but you get the idea. You've got to know how to find the center of the circle in space, which is different from that division, major axis, that divides the ellipse into perfect symmetry. Okay? Do you kind of get that point? Anything I should clarify on it? Some of you already knew this. Go ahead, Dan.
Okay, so just to find.
No, you wouldn't even deal with the square if you were drawing the ellipse.
The box, whatever is in like tilted in space, right? Or just the square tilted in space. The one you got the ellipse in, right?
Okay.
But to find the center, it's totally different. So you draw diagonal lines.
You can draw diagonal lines from the box. There's another way to do it, and that's eyeball it. Right? You get to know after you've done this a bit that the center is going to be a little bit. You can kind of, between there and there, that looks about right. You get an eye for these things. I found that after having done tons of hours of paste up in 1981 to 83, that I can estimate quarters of an inches, and sixteenths of an inches so accurately by eyeball, and that I can tell, whether something's squared up by eyeball. I can get it almost exact because I did it so much. Right? And there's something that happens with this too. You measure this stuff, you learn it, and then eventually you can eyeball it. Now, all of this business that I've been talking about, phonograph records and buckets and stuff, last week and this week, all of it has been conveniently placed on a nice vertical line, which is great. A lot of stuff, when that cup is sitting down there on a nice vertical line, it's very simple. It means that you can draw cylinders like the multi-tiered wedding cake on that nice vertical line and know that as they go over, your eye level. Eventually they will be at your eye level, and then eventually they will go below your eye level. And so you'll know how to place those ellipses on there, right? And you can build on that. And it also allows you, if you are drawing something that is not just cylinders. Let's say it's a little more complicated than cylinders. Let's say that we'll try to carve it out of a cylinder to make a point here. That you've got something that's shaped a little more complexly, that it might be shaped something like this, but it's still going to follow the same basic rules that those cylinders are going to be more open. And if you've got a dome in there, if you've got parts that dip in or that dome up or whatever, you're still going to wrap lines around there like that, so that if you've got the top of a teapot, for example, and you can see into that teapot like that, and then maybe there's a little part that comes up out of the teapot like that with a little knob on it. All of these conveniently conform to that vertical line. We know how to place the ellipses. The minor axis fits right there. And it's the same way, isn't it? If you take the board and go like that, and you make it so that now these are ellipses that are fitting on a cylinder that is going horizontally. And this could be, you know, any number of things. It could be pipes laid down. It could be the railing on at the edge of the roller rink that people are leaning against. You'd know that there's some place like that and some place like that. And as it gets further away from you, those ellipses become more open. But again, your ellipses are going to be placed with their minor axis running right along that line, because it's in one-point perspective. And if you tilt these cylinders, it's still easy for you, isn't it? Is the fan still on that thing? Could you turn it off? If you tilt this cylinder so that it's in a position like so, or even if it isn't a cylinder, it can be a cone like that. You know how to place that on there, right? It's going to be like so. And if that's severe, that's got to be even more open than the front one. But here's where you get into trouble. If you've got a nice vertical line or a nice horizontal line or a cylinder that you know is a cylinder tipped like that, you know how to place that ellipse. But you run into confusion when you have a car or a barbell or whatever else that's not in one-point perspective. If you've got a car that we'll say is in two-point perspective, we'll fit the car, say that the car would fit into this box, and we could carve out of it. Actually, let's make it a kind of a chunky car so that I can make the wheels big enough to make this point a little better. Let's fit it into something about like so. If you've got wheels right here, right, they're going to fit somewhere in there, and you want to place that ellipse, what the beginner tends to do something. They tend to put the ellipse so that it's like this. It's wrong. What do you have to do? Anyone know? This ellipse is not placed correctly. It looks wrong. If it doesn't look wrong to you, it will if you'll spend this week looking at how these ellipses look. Let me amplify it by drawing a cube here, like so. Remember, the major and minor axis of the ellipse have to be at right angles to each other. But if you put an ellipse in there, it won't fit, for one thing. I mean, if you get it wide enough to go out there, it's going to end up coming up there. You know, you're going to have trouble making it hit at the right points. What are the right points? Find the center, and that line will go back to that vanishing point. That one will go over to that vanishing point. That will be the center. And the ellipse, the circle in perspective, has got to touch the line right there, right there, right there, and right there. Okay? Here is the secret to this. This is the trick. But I want to make sure, because this can confuse people. That's which axis? Major axis of what? The ellipse. That's what? Minor axis of what? The ellipse. This is what? Major axis of what? Of the whole cylindrical cone shape. Which means this is what? Minor axis of what? The whole cone shape. Major simply means the long one. This is the long one of the ellipse. This is the short one of the ellipse. And likewise with the cylinder. This is the long axis. That's the major axis of this whole cylinder shape, and that's the minor axis. Okay, we've got to make that point clear, because here's the way you place this stuff. You imagine it being the end of a cylinder. Just like that. Imagine it being the end of a cylinder, and the cylinder has a major axis that should become the minor axis of the ellipse. Did you follow that? That's the trick. So, where would the cylinder go? It would go back that way, right? And we'll say if that's the center point there, it's going to go back like that. Now watch what happens. You take that line, and you do one that is perfectly real right angles to that, and construct your ellipse on that, and you will get a line that will really be the way it looks. I'm going to do it on the side of, we'll make this thing like a steamroller. Do you see how that looks more correct? It's a huge wheel, granted. But
you could follow the perspective line together. When I was thinking, doing that, I was following the perspective line going this way.
Going this way?
Yeah.
Okay, and here's the thing. They tell you to think of it as the end of a cylinder. Where does the cylinder go? It's going back. Here's a better way. I like this better than the cylinder metaphor. Think of it as at the end of an axle. Think of it as a bell on a barbell. The bar, if it's the bell, the bar has got to go off that way. Bar's not going off that way. It's the end of a barbell. You find the center, and then you run that axle line back to that vanishing point, and then that will be where you put a right angle to it, and that ellipse will fit there just beautifully and hit right at the right points. How will you do it for this side? Then, if it's going to be that this is the end of an axle, right? Where's the axle going to go? Which way? Point to it. Where's the axle for that way? So you figure that's about the middle there. Run that axle off to that vanishing point, and look what happens. Then find true right angles. It's got to be right angles when you draw an ellipse. True right angles. This will be a little more open ellipse than that, but it will fit on there so that it touches at the right place. Actually, the problem I'm running into is that this is not a true square in perspective, so I'm ending up having to distort it. But as far as the placement is concerned, if it was a true square at that angle, it would be more out here. And by the way, that's one of the ways you can find out whether it's a true square, is that if you draw an ellipse from an ellipse template that's accurate, and then you get the lines right and find your vanishing points, it would have to be a true square. Got to get that at a right angle too, and it will fit on there so that it's correct. And I'm going to show you this with slides that have been done with templates and all, so that you'll get the point better. In other words, let's say that we've got a bar coming out of the front of this thing. If we've got it coming out of the front of this thing, it's going to be the end of a cylinder, right? It's going to be placed like that. That is major axis or minor axis, major axis. Minor axis becomes the same as the major axis of that cylinder. This is a mess. Let me do it again. That will be the more foreshortened side. That will be the more open side. I'll try to make this a pretty accurate cube. That ought to be close enough. This one, I can swing it in there knowing. Did you see? Now, see, subconsciously, I've got it built into my brain that the major axis went like that and the minor axis went where? Like that. Do you see how it worked? It's going off that way. I didn't try to make it stand up straight. And if I want to do that one, I can kind of figure the major axis is going to have to be like that because the axle would go, and then I can kind of fit it on there. Actually, it would be right about there. Oop. That's how I tested. That is not, I still did not get an accurate cube. It's off that much. This is not an ellipse. It's more like an egg shape. I'm trying to shave it in there when it ought to be like so. Oh well, you know, you try. You fail, you get your templates out. Does this make sense, what I'm doing though? The placement of this ellipse. Think of the minor axis as the end of an axle. And that axle goes off into space. Minor axis, end of an axle. Axle goes off into space in 2 point. Now, I had this problem many times in trying to place ellipses, and I never figured it out on my own. And it was in 1986 that I was sitting at a bus stop on Magnolia in the afternoon, waiting for the bus, reading Ernest Watson's book. And I was in the chapter on circles and ellipses, and I read that section and got it. That's how you do this. And I thought, I've got to test this. And I was watching cars drive by, and I would watch the wheels of the cars. Remember, the cars, unless they're right there, profile to you, in which they're in 1 point perspective, when they're coming toward you from your right, coming toward you from your left, as you turn your head, they're in 2 point. And I would notice that as I'd watch the angle of the ellipses that made those wheels, they were at an angle like this, and then as they'd come in front of me, they'd go like that and become a circle, and as they'd go away from me, I could see them tilt. And even though I was sitting at a Magnolia bus stop inhaling people's exhaust fumes, it was sort of a blissful feeling. Because I was seeing it works. This is the trick to how ellipses get placed on objects that are not in 1 point. That's the way you do this, and that's how come we built these things for the perspective class and drew these in every conceivable position and then tried to find, see, that line and that line are not the lines for making the ellipse. These are lines for figuring out how the circle is divided, and you will find in your imagination, you will find where the lines are to make this business. And one of the secrets is if it's in 2 point perspective, that minor axis must go back like the bar on a barbell. It's going to go back there like that, along that line. And then if you can always think that way, there you've got your symmetrical ellipse. It will go on like that.
You know, the way to think of that is having two pieces of cardboard like this. You know?
Oh, yeah, okay, right. So that you know you distinguish between 2 different planes. This plane would go back like that. This plane would go back like that. Okay. Oh, another thing about this that you should know. I'll try a third time. See if I can get this to make this point. Let's imagine it as a clock face. Clock face in 2 point perspective. We want to find the center of that. That's where the pivot is going to be for the hands. It's got to touch at these 4 points. How will we know? We've got to run a line like that, and that will be the minor axis. I have a feeling I'm going to get in trouble. Nope, it's working this time, folks. I'm doing it. I can't believe it. Okay, we've got a pretty close to a circle in space there. A little bit of forcing it at the edge. Little problem right there where we need to pull it out. Remember, major axis, minor axis, right? You know how we found the minor axis. Remember what we talked about at the beginning. That has nothing to do with where the center is. We need to know the center, and we need to place the angle. I've been talking for the last 15 minutes about placing the angle of the ellipse. Let's get back now to knowing the center. There's the center. That's the center of the ellipse, but there's the center of the clock from which the hands will come out. Where is 12 o'clock? Is 12 o'clock there? No. So that means the major axis has nothing to do with up and down. You would find the major axis, or where 12 o'clock is, by finding the middle and running a vertical line parallel to those like that. And that's where 12 o'clock will be, and that's where 6 o'clock will be. What about 3 o'clock and 9 o'clock? You know that they're not going to be here and here, where the minor axis of the ellipse is. How do you find them? You run a line halfway, you just measure, halfway down, or you can run through that point back to that vanishing point, and that line is going to go off to that vanishing point, and that's where 3 o'clock and 9 o'clock are going to fit. The point is, these crosshairs, this perfect symmetry, is only for drawing the ellipse. It has little to do, nothing to do, with where the center point of the circle it represents is, nor where vertical and horizontal are on the circle that it represents. Okay? Does the major axis go through the center? On this one, no.
No, the minor axis.
Does the minor axis go through the center? Not necessarily, no. Although it comes so close that you kind of, there's only one way that a true symmetrical ellipse will fit on there. And it depends, it has to do with the severity of the angle. But yeah, you'll find that I just go through the middle to kind of place it generally, and then you're going to have to refine it down. Which brings up a point. To make practical use of this, the problem with anything scientific like this as it relates to art is that you can easily experience paralysis by analysis. That is, you start thinking about all this stuff when you're starting a drawing. Don't. Unless you're doing a technical cutaway of an airbrush, right? Which you've got to start thinking, and the major axis is going to be like that, the ellipse is going to be point of view like this. If you want to evade paralysis by analysis, I suggest sketch first and then correct it later. A novelist was trying to write the perfect novel, never got beyond the first. He'd been working on the first paragraph for years. The reason why is because he was trying to write the perfect novel. He shouldn't have been doing that. He should have been trying to tell a story, jump into the story, do the story, and then you go back later and say it's got problems here and fix those, and then you go back and got problems here and fix that. But as soon as you're trying to place everything perfectly, you will not create any more than you will be able to speak if you're thinking about grammar. Does that make sense? Sketch first, get it in there the way it's got to get in, and then later go in and say, this is wrong, shift that there. So you will be surprised how much it might change. But you don't start out thinking this way. Jump in first. That's if you want to make practical use of this. There is another harder, longer-term way. It's called mastering this. And it takes more than a few weeks. But if you want to master this, where you can draw like this, where you've got all of the stuff correct, as easily as you speak, and the grammar comes out right, as easily as you walk without tripping, which you did a lot when you were an infant, if you want to draw with that kind of effortlessness and get it right, then you've got to do something that Ernest Watson in his book said that he recommended this ratio of theory to practice. 1 part theory, 1 part of what we're doing here. How many parts practice? Anybody read it? 50 parts practice. That's a bit much. 15 would help you a lot. You know, 1 part theory, 15 parts practice, 20 parts practice. He said 50. And of course, he's coming from the old school where to be trained, you had to do this effortlessly, like a master. I went through Nicolaides. I got about 75 hours in the Nicolaides book, The Natural Way to Draw, in which he had you do hours and hours of gesture drawing. And one of the things that I did gesture drawing from at that time was a telephone cord. It wasn't just gesture drawing. I'm sorry, I meant to say that he had you do cross-contour drawing and do things where you're trying to wrap lines. You're looking at the object and you're kind of doing this, you know, and trying to wrap lines around there. And so I would look at a telephone cord, which is a pretty complicated thing. You know, it's a helix, and it's got distinct planes that curve like so and then like so. And I was doing my contour drawings by looking at that, but I hadn't studied perspective intensely, and it helped me. It helped me because I started to think about space on paper. It would have helped me more if I would have been studying perspective and then doing my Nicolaides. And that way I'd be thinking about the placement of these ellipses. And what happens when you do that? You drive it into your subconscious mind so that eventually it does become effortless. That's the way you master it. You can make it practical by just sketching first, correcting the problems later, but I suggest that if you want to be a master, that the long-range thing that you shoot for is to get it so that it's natural to you. Here's how you can test whether you've got it. If you can take a sphere, if you can take a circle and say that's not a circle, that's a globe, and you can tell where the top point is and where the bottom point is through there, and you can wrap those ellipses around there to place how far it's tipped down. And if you can slice that thing one way or another, say I'm going to take a slice across there, and know how that slice would look and be able to place it without using templates and slice all different angles, then you've got this part mastered, this circles and ellipses business. Okay?
This is an oxygenator I drew and rendered with airbrush. I did the outlines with ballpoint pen. Its basic construction is a cylinder. All of those tubes that have been cut away are cylinders, and the ellipses that describe their cross sections are placed according to that axle analogy. The lower ones tip more than the upper ones because the minor axes on the lower ones go up to a vanishing point more severely than the upper ones.